Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today we are going to study and learn the topic of elastic constants. Now we can see these are the Poisson's ratio of common materials. For aluminium, Poisson's ratio is 0.33. For brass, it is 0.340. For bronze, it is 0.35. And we can see the maximum Poisson's ratio in this among all these materials we observe for copper. For copper material, the Poisson's ratio is 0.355. Whereas for another material, for cork, it is 0. So Poisson's ratio for cork is 0. The cork material is used for insulating, electrical insulation purposes. These materials are used. For concrete, it is 0.2. For concrete, it is 0.2. Now, the next relation between elastic constants, that is E and C. Here, what is E? E for modulus of elasticity. Modulus of elasticity. Whereas C is modulus of rigidity. C is modulus of rigidity. Now here, what is the relation between these two elastic moduli, E and C? So to understand this relation so let us consider a component or a beam or a body here L, M, S, T. This body is subjected to a shear force. F we applied. What is the shear force? The force which acts parallel to the cross section of this MS layers. Parallel to the cross section. Then because of applying the load F, and there is complementary shear stress occurs on the surfaces L, M and ST. The complementary shear stresses are here tau. So the body should be in equilibrium such a way this complementary shear stress and it is balanced by at fixed end LT. And on the surface of MS, shear stress is balanced with ST. So these are the complementary shear stresses acted. After that it is in equilibrium. So because of this application, the M moved to M dash and S moved to S dash. Okay. And along the diagonal of MT there is a compressive stress. And along the diagonal of LS there is a tensile stress. So because of the shear force acting on the surface MS, then there is the compressive and the compressive stress and tensile stresses are acting internally, the stresses develop. Now because of the tensile stress, there is a deformation. That's why S went to S dash. And because of the compressive stress, there is reduction. That's why M is compressive to M dash. Now the new body after compressive load is L, M dash, S dash, T. So the angle made after applying the shear force, that is a phi angle. This phi gives the shear strain. Shear strain phi equal to the shear strain phi equal to S dash by ST. Now here the shear strain phi equal to S dash by ST, and also shear strain, that is a tau by C. Tau means shear stress by modulus of rigidity. Modulus of rigidity is denoted by C or G or N. Now the modulus of rigidity C equal to shear stress by shear strain. From this, phi equal to shear stress by modulus of rigidity. Now, the equation that is starting, the equation 1, that is SS dash by ST, and this is, you consider it the equation 2. Both are shear strains. After equating 1 and 2, that is SS dash by ST equal to tau by C. Now, on the diagonal, if we consider the diagonal, that is LS dash, this is LS dash. A perpendicular line we have drawn, that is SN. So, now diagonal strain NS dash by LN, from this NS dash by LN, the deformation, change in length by original length, NS dash by LN, that equal to, this LN is nothing but a length LS, diagonal length. Now, NS dash by LN equal to LS, so LS. This is another relation. Now, if you have to substitute in the place of NS dash in terms of SS dash, then this is the triangle L, right angle triangle SNS dash. From this, NS dash equal to SS dash cos 45. SS dash 45 equal to NS dash. Now, what is cos 45? Cos 45 equal to 1 by root 2 SS dash by root 2. Now, from the triangle here, the angle LS dash T is assumed to be equal to, that is LST. Now, whereas here, since the SS dash is very small, so that LS equal to ST times root 2. Now here we know the LS, that is ST times root 2. You substitute this LS in the above equation. The equation here it is NS dash by LS. This NS dash value and LS value, both if you substitute here, that is SS dash by 2 times ST. Now we know that SS dash by ST equal to shear strain. Now that is nothing but, that is shear strain equal to shear stress by modulus of rigidity. Now the diagonal strain is in terms of shear stress and the modulus of rigidity, that is tau by 2c. The tau by 2c is equal to the shear stress here. It is diagonal strain. The diagonal strain, what is the diagonal strain equal to? The normal stress, it is compressive and shear tensile stress are acting. That is nothing but that is normal stress, that is sigma n by 2c. Now, from the fundamentals of when the stresses, complementary stresses are acting, so the normal stress due to shear stress, the net strain along LS, that equal to sigma n by E plus mu times sigma n by E. The shear Poisson's ratio is denoted by mu or 1 by m. So here sigma n by E times plus 1 by m times sigma n by E. So make it common, this sigma n by E, then 1 plus 1 by m. Now comparing the equations sigma n by 2c. This is sigma n by 2c diagonal strain, sigma n by 2c equal to the diagonal strain, another equation sigma n by E times 1 plus 1 by m. Cancel this sigma n, sigma n. From this equation, E equal to 2c times 1 plus mu or 1 plus 1 by m. This equation can also be written as 1 plus mu. E equal to 2c times 1 plus mu. This is the relation between elastic moduli of modulus of elasticity and modulus of rigidity. That is E equal to 2c times 1 plus mu. Now what is the E units? Units for E is Newton per meter square. Our modulus of rigidity is Newton per meter square. So what is the units for Poisson's ratio? Is no units. It is the ratio. So the relationship between modulus of elasticity and modulus of rigidity is E equal to 2c times 1 plus mu. Next, there another relation, the relation between E and K. E for elastic modulus or modulus of elasticity or Young's modulus, and where K for bulk modulus, where K is for bulk modulus. So, if they say the solid cube, it is subjected to normal stress, normal compressive stresses sigma n on all the faces, then the relation, the direct strain in each axis, that is, here we can see that sigma n by E in compression, and the lateral strain that equal to lateral strain in other axis that equal to sigma 1 by m times sigma n by E, that is in tensile direction. Now we can understand that what is the net compressive strain in each axis. The net compressive strain in each axis, that is, we are considering here it is a cube. Cube means in x, y and z directions. So along in one axis means another axis becomes negative. That is sigma n by E is in tensile, remaining or in compressive. That is sigma n by E minus 1 by m times sigma n by E, minus 1 by m times sigma n by E. That is finally sigma n by E times 1 minus 2 by m. Now what is volumetric strain? The volumetric strain that equal to, it is denoted by EV or epsilon V. That equal to 3 times linear strain. The linear strain is already obtained here. That is along in the linear strain. The linear strain can be compressive or tensile. Here the linear strain is the net compressive strain, that is sigma n by E times 1 minus 2 by m. Substitute that one here, the linear strain place. Then 3 times sigma n by E 1 minus 2 by m. Now we know the bulk modulus K equal to the normal stress by volumetric strain. From this equation, volumetric strain equal to sigma n by K. That sigma n by K, that is EV or epsilon V. EV equal to sigma n by K. We know that EV already sigma n by K and EV equal to 3 times sigma n by E times 1 minus 2 by m. So equate these two. This is also volumetric strain, this is also volumetric strain. By equating these two, we can obtain the relationship between two elastic constants such as E and K. That is sigma n by K minus 3 times sigma n by E 1 minus 2 by m. Sigma n cancel. Then from this equation, E equal to 3K times 1 minus 2 by m. This is the relation between E and K. So here, what is the proportionality? If we interpret the relationship between E and K, here here 1 minus 2 by m is a constant. 3 times 1 minus 2 by m is constant. Then it is E is directly proportional to K. When modulus of elasticity increases, the bulk modulus also increased. Then the relation, the third part is that the relation between 3 elastic constants here. The 3 elastic constants are E for modulus of elasticity, it is modulus of elasticity, C modulus of rigidity, K bulk modulus. So far we studied what is the relation between E and C, what is the relation between E and K. Now we are going to find the relation between E, C and K. We already found E and K relationship, that is E time E equal to 3K times 1 minus 2 by M. And another relation is E equal to 2C times 1 plus 1 by M. Equate these two or find out. Then if you equate these two equations, suppose it is equation 1, equation 2. If you equate these two, then we will find out the relation between C, K, mu. But we want a relation between E, K and C. So what is the here value? In the place of M equal to, if you make it equation, that M equal to, find out and substitute in equation 2, then you can find the relation between E, C and K. Now M equal to, what is M equal to? 2C times, from this equation 2, that is M equal to 2C by E minus 2C. Substitute this M value in equation 2. Then E equal to, in equation 1, substitute this M value in equation 1. Then E equal to 3K times 1 minus 2 by, that M is 2C by E minus 2C. Now, if we simplify it, then E equal to 3K times, then 2 get cancelled, then 1 minus E minus 2C by C. Now E equal to, then E by 3K equal, E by 3K, then E by 3K equal to, make it LCM C minus E plus 2C by C. Then in this 2C plus 2C plus C, that is 3C minus E by C. E by 3K equal to 3C minus E by C. Then E by 3K, make its further simplification 3 minus E by C. If we send left side, E by 3K plus E by C equal to 3. From this make it common E. Okay, E make it 1 by 3K plus C, that is EC plus 3KE equal to 9KC. E make it common, E times 3K plus C. E times 3K plus C equal to 9KC. Then finally E equal to 9KC by 3K plus C. So these are the relationship between E, K and C. E-KC relation. Now in this, so far we calculated relationship between EKM, EK mu, and that means Young's modulus, bulk modulus and Poisson's ratio. Another relation is Young's modulus, modulus of rigidity and Poisson's ratio. And the third one is relationship between modulus of elasticity, modulus of rigidity and bulk modulus, EC and K. So these are the three relations are very important for elastic constants. Now here further interpretation from these relationships, that is E equal to 3K times 1 minus 2 by M. Another relation is E equal to 2C times 1 plus 1 by M. And another relation is E equal to 9KC by 3K plus C. So if we equate, suppose if we equate equation 1, suppose if we consider equation 1, equation 2 and equation 3. Equate equation 1 and equation 2. Then 3K times, I am writing in the place of 1 by M, also equal to mu, denoted by. So 2 mu equal to 2C times 1 plus 2C times 1 plus mu. From this relationship, we can study that K equal to 2C times 1 plus mu by 1 minus 2 mu 2/3 of C times 1 plus mu by 1 minus 2 mu. This is the relation between elastic constants K, C and mu. Bulk modulus, C for modulus of rigidity and mu for Poisson's ratio. So this is the relation between bulk modulus, modulus of rigidity and Poisson's ratio. K equal to again 2C by 2/3 of C times 1 plus mu by 1 minus 2 mu. Now, if you equate equation 2 and equation 3. Now the fourth equation we will write here K equal to 2C by 3 times 1 plus mu by 1 minus 2 mu. This is the fourth equation. Now if you equate equation 2 and equation 3. Equation 2 and equation 3. Let us see what is the relation between Kc and mu. Equation 2 equal to 2C times 1 plus mu and equation 3 equal to 9 Kc times 3K plus C. Now from this K we want how to make it K common? Make it K common. 9 Kc by 3K plus C. That is 2C times 1 plus mu 9 Kc by 3K plus C, that is 9 Kc by 3K plus C, make it this side 3K plus C. So from this 9C, then from this K equal to 3K plus C times 1 plus mu 2C by 9C. Now again here K is common here. So such a way that we can see the relation between the both. If we simplify further the equation 2 and equation 3, if we make it, and similarly equation 1 and equation 2, then if we can obtain the same relation as we have obtained here 4, that is 2C by 3 times 1 plus mu by 1 minus 2 mu. So here again the summary for in this class, the Poisson's elastic constants. The elastic constants are, there are 4 in number. Number 1, Poisson's ratio. Poisson's ratio, it is denoted by mu or 1 by m. I will write here Poisson's ratio. Second elastic constant is modulus of elasticity. This is modulus of elasticity. The third elastic constant is modulus of rigidity. It is denoted by G or C or N. It is modulus of rigidity. The fourth elastic constant is bulk modulus. It is denoted by letter K. Bulk modulus. Modulus of elasticity, that E equal to normal stress by normal strain. If it is compressive, modulus of elasticity sigma C by epsilon C, compressive strain. If it is a tensile, sigma n by tensile, sigma t by epsilon t. Modulus of rigidity, C denoted by C, G or N, that is shear stress by shear strain. And bulk modulus, K equal to normal stress by volumetric strain. So these are the four elastic constants are highly useful in order to study the behavior of material and material properties. The material properties are ductility, brittleness, hardness, malleability, fatigue, toughness, creep. So those properties can be studied analytically and also experimentally. Through experimentally, we can study the behavior and material properties by using various testing machines. For tensile test is used for studying the tensile strain and percentage of elongation and the stress at yield point and modulus of elasticity and also the stress at ultimate, the tensile strength at ultimate sigma ut, ultimate tensile stress point, that is sigma ut. And this bulk modulus, whereas the shear modulus can be studied by using the spring testing machine, and also we can study by using tensile test by changing the setup UTM, universal testing machine, by adding the shear testing attachment. Then we can also study the modulus of rigidity of a material by using universal testing machine. And Poisson's ratio, this Poisson's ratio also can be studied by using universal testing machine. So in this class we have studied the relationship between E and C. E and C, modulus of elasticity and modulus of rigidity, and also modulus of elasticity and bulk modulus, and also the relationship between modulus of elasticity, modulus of rigidity and bulk modulus. So the relation between modulus of elasticity and bulk modulus is obtained as E equal to 3k times 1 minus 2 by m. The relation between modulus of elasticity and modulus of rigidity is E equal to 2c times 1 plus 1 by m. The relationship between modulus of elasticity, bulk modulus and modulus of rigidity is E equal to 9kc by 3k plus c. In the equation, the relationship, in this relationship, there is no Poisson's ratio. But in the relationships of E and K and E and C, there is Poisson's ratio, that is 1 by m. But the relation which doesn't have the elastic constant, the Poisson's ratio, is the formula is E equal to 9kc by 3k plus c. And there is no bulk modulus, but there is modulus of elasticity and modulus of rigidity and Poisson's ratio. That relationship is E equal to 2c times 1 plus 1 by m. And there is no modulus of rigidity, and the relation only modulus, bulk modulus and modulus of elasticity and Poisson's ratio, Ek 1 by m. This is the relationship. So by using these three relationships and equating combinations, 1 and 3 equations, 1 and 2 and 2 and 3, and equating, we can obtain different relationships of between different elastic constants. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.